Okay, so now let's use this assumption, this IID assumption, to motivate something called the Bayes classifier. Is it possible to talk about what an optimal classifier would look like using this assumption of our data coming to us IID from nature? The answer is yes, and it's going to motivate something called the Bayes classifier. The theory here at a high level is only going to motivate why a Bayes classifier might be the right thing to do, but we aren't going to then be able to say that we actually found the optimal classifier. So this is motivating a direction for how to develop a classifier called a Bayes classifier. So again, we'll assume that our data has come to us IID according to some distribution where we're getting the labeled pairs simultaneously IID. So there's a joint distribution on both the covariates and its label. So there's a joint distribution on the contents of the email and the label of whether it's a spam or non-spam email. And so we're going to use this distribution, even though we don't know what it is, we can still reason about it in the following two ways. So first, let's discuss what is the expectation of the indicator of an event. So we need to discuss this before we can proceed. So here are two quantities that we could, in principle, calculate with this underlying distribution if we had access to it. So we can't actually calculate these things, but we can still reason about them. So first, what is the expectation of the indicator of an event? So what is the expectation under this unknown distribution that we obtain a y, a label, equal to 1? So we're thinking about binary classifiers for the moment. So the expectation under P of our label being equal to 1 is simply the probability that the label equals 1 according to this distribution. So we integrate out x and we get a probability on the label being either 1 or 0 or some other number. The expectation of the indicator of the event is equal to the probability of the event under the distribution that you're using to calculate the expectation. So this is a general principle. The second principle is about the Tower property of conditional expectation. So conditional expectations can be viewed as random variables. So what does this mean? Let A and B both be random variables. Therefore, the expectation of A given B can be viewed as a random variable as well. So what this expectation is calculating is the expectation of A. So we integrate out all uncertainty of A, condition on a particular B. So for a specific value of B, we get the expectation of A and call that C. However, because B is now a random variable, this expectation also becomes a random variable. So we randomly generate a B, plug it in here, get our expectation of A. But because B is random, this expectation now is also random. However, the expectation of this random variable gets rid of all the randomness. So the expectation of C, where this is integrating over B, is equal to the expectation of the conditional expectation of A given B. That's simply equal to the expectation of A, where B now has been integrated out. So this is a very important property of conditional expectation called the Tower property. Expectations of conditional expectations remove the conditioning, essentially. So let's use these two properties to calculate what an optimal classifier might look like. So of course, before we can say something is optimal, we have to say what we're optimizing. So in this sense, we're going to say that the optimal classifier is the classifier that minimizes the probability of making a mistake, according to the assumption that our data is IID from some underlying distribution. Okay, so what we're saying here is that we want to minimize the probability that our classifier, whatever it is, does not predict the label of x to be equal to what its true label is. So remember that x and y are both generated from a randomly from some underlying distribution. They're independent from any other labeled pairs. So we're thinking of generating a labeled pair, generate a random x and its associated label y according to the underlying distribution, and then look, does our classifier actually predict the label of x to be equal to what the label turns out to be? Now calculate the probability of that by integrating over the distribution p. So from the previous slide, we can say that the probability that our classifier will make a mistake is equal to the expectation of the indicator that our classifier makes a mistake, where this expectation uses the true underlying distribution p to calculate it. And then the Tower property of conditional expectation lets us say that we can first calculate the conditional expectation of this indicator given the value of x. So let's first pretend like we know the value of x, and then say for that specific value, what is the expectation of the indicator that I don't predict the label correctly? And then take the expectation of that. So this might be a bit confusing. Why is this a random variable? So our classifier is not random. Given x, f of x is not a random variable. So our classifier will always predict the same label for a particular x. However, we assume that the underlying distribution does not have a deterministic distribution on y given the x. So for example, the same email might 95% of the time truly be a spam email, but 5% of the time that exact same email might not be spam. So you could imagine conditions where that were the case. So in this sense, y is what's random, and that's why this is a random variable. And now when we take the expectation of that, we get rid of the impact of x. Okay, so let's expand this inner conditional expectation. So for some specific point x, so for example, evaluating this conditional expectation at a specific value x, we can expand the expectation this way. So this right-hand side is literally equal to this left-hand side, where we're taking the expectation of the indicator that we get that our classifier gets it wrong at this particular x, using the distribution, so the conditional distribution of the probability of y given the x that we're evaluating at. So x is fixed, but now y is random. So we evaluate this conditional expectation here. Okay, so our goal now is for every point x, so point-wise, we want to minimize this function over each point x. So in order to minimize it, what that means is that our classifier is going to assign one of k possible labels to every point x. And so that means that this is going to be equal to 0 only for one value of y. So what this is really doing is saying for the label that we assign to x, sum up the probabilities of all of the labels other than the assignment. In other words, sum up the probability that we get it wrong. So if we want to minimize this equality, we can do so by assigning the label to x to be the most probable label according to nature. That way this is equal to 0 for the maximum value here, and then we're summing up the smallest, the k minus 1 smallest probabilities according to this distribution. So again, our Bayes classifier, this is called a Bayes classifier, is for a particular input x, predict the label to be the most probable label conditioned on x according to the true underlying distribution given to us from nature. So what we can show is that by making this prediction, that the Bayes classifier will have the smallest prediction error among all possible classifiers. So if we get our labeled data as IID from some underlying distribution from nature, and then for every single x, we predict the label to be the most probable label according to that that distribution, then we're going to minimize our probability of making an error. So of course the problem is we don't know what the underlying distribution is from nature, so we don't actually know what this distribution is, so we need to somehow approximate it. And that approximation is going to therefore not allow us to say that we have the optimal classifier anymore.